Chapter 1. The Night the Sky Fell. Hello curious minds, and welcome to an extraordinary journey through time. Tonight, we are going to explore one of Earth's greatest mysteries, a story so incredible that scientists are still arguing about it today. Picture this. 12,900 years ago, our ancestors looked up at a clear night sky, just like you might do tonight. But what happened next changed everything. Some scientists believe a visitor from space crashed into our planet with the force of millions of nuclear bombs. Others think the Earth simply stumbled over its own climate system, like a person tripping in the dark. This is the story of the younger Dryas, the day the Ice Age came back from the dead. Before we dive into this incredible tale, I want you to know something important. If you're listening to fall asleep, that's perfectly fine. I've organized this story into clear chapters so you can always pick up where you left off tomorrow night. And if you're finding this story as fascinating as I do, please consider hitting that like button and subscribing. It really helps more people discover these amazing stories from our planet's past. Now, let me paint you a picture of the world as it was 13,000 years ago. Imagine walking across what would one day become New York City, but instead of skyscrapers, you see endless grasslands stretching to the horizon. Massive woolly mammoths, bigger than modern elephants, graze peacefully in herds. Saber-toothed cats with fangs like curved daggers stalk through tall grass. Giant ground sloths the size of small cars lumber past, completely unaware that they're living in the final chapter of their species' story. The air is crisp, but getting warmer. For thousands of years, giant ice sheets had covered much of North America and Europe. But now, those glaciers were finally retreating. Rivers of meltwater carved new valleys. Green forests crept northward into lands that had been frozen wasteland for millennia. To the small bands of humans scattered across these continents, it must have felt like the world was waking up from a long, cold sleep. They crafted beautiful stone spear points, hunted the giant animals, and for the first time in generations, they could dare to hope that the endless winter was finally ending. But the Earth had one more surprise waiting, a surprise so dramatic that it would change the course of history forever. What happened next was so sudden, so catastrophic, that it's taken scientists over a century to peak. Age for hundreds of thousands of years suddenly went extinct. Human cultures that had flourished for centuries vanished almost overnight. But here's the truly mysterious part. While the North froze, parts of the Southern Hemisphere actually got warmer. It was as if someone had flipped a switch, dividing the planet into two completely different worlds. What could cause such a dramatic change so quickly? Was it really a cosmic visitor that arrived without warning? Or was it something far more subtle? A chain reaction in Earth's own climate system that we're still struggling to understand. As we explore this mystery together, we'll travel from the frozen archives of Greenland to the ancient ruins of settlements that were abandoned overnight. We'll examine tiny diamonds that might have formed in cosmic explosions, and mysterious layers of black sediment that appeared across 3 continents at exactly the same time. Most importantly, we'll discover why this 12,900-year-old mystery matters so much today. Because if Earth's climate can change this dramatically, this quickly, what does that mean for our future? Coming up next, we'll meet the giants who ruled the Earth just before this catastrophe struck. Creatures so magnificent that losing them changed the very nature of our planet's ecosystems forever. Chapter 2. When Giants Walked Among Us. Close your eyes and try to imagine the most incredible zoo you've ever seen. Now imagine that instead of cages and enclosures, these amazing animals roam freely across entire continents. This was the world of the late Pleistocene, the age of giants. Just 13,000 years ago, North America was home to animals that would seem impossible today. Woolly mammoths with tusks that curved in perfect spirals grazed on vast grasslands. These weren't just big elephants, they were perfectly adapted Ice Age survivors with thick fur coats and small ears to prevent heat loss. But the mammoths weren't alone. Imagine coming face to face with a short-faced bear, a creature that stood 11 feet tall on its hind legs and could run faster than a horse. Or picture the American cheetah, built for speed on the open plains, chasing herds of wild horses and camels that had evolved right here in North America. The most incredible of all might have been the giant ground sloths. Some species grew to be over 20 feet long and weighed as much as modern elephants. Unlike their tiny tree-dwelling relatives today, the continents tell slightly different versions of this story. In South America, giant armadillos called glyptodons roamed the pampas. These weren't like modern armadillos. They were the size of Volkswagen Beetles, with shells so thick they were practically tanks. Massive saber-toothed cats called Smilodon fatalis hunted in packs, taking down prey that would dwarf any animal alive today. Europe had its own cast of giants. Woolly rhinoceroses with horn spans wider than a person's outstretched arms shared the landscape, with cave bears so large they made modern grizzlies look small. Giant deer, misnamed Irish elk, carried antlers that spanned 12 feet from tip to tip. But here's where the story gets really intriguing. The timing of when these animals disappeared isn't random. Across the globe, the largest animals started going extinct around the same time that humans began spreading to new continents. In Australia, the giants disappeared about 50,000 years ago, right when humans first arrived. In the Americas, the extinctions cluster around 13,000 to 11,000 years ago. This has led to one of paleontology's biggest debates. Did humans hunt these animals to extinction, or was something else responsible? For decades, scientists have argued about this overkill hypothesis. On one side, supporters point out that wherever humans went, large animals disappeared. They argue that these animals had never faced human hunters before and simply weren't prepared for such efficient predators. But there's a problem with this simple explanation. Many of these animals were incredibly dangerous. A mammoth could easily kill a human hunter with a single swing of its trunk. Saber-toothed cats were apex predators themselves. How could small bands of Stone Age hunters possibly drive such powerful creatures to extinction? This is where our story gets even more mysterious, because the timing of these extinctions, particularly in North America, coincides almost exactly with the sudden climate change we call the Younger Dryas. Was it coincidence that the giants disappeared just as the climate plunged back into near Ice Age conditions? Or was there a connection that scientists are only now beginning to understand? Some researchers have proposed that it wasn't humans alone, or climate change alone, but a deadly combination of both. The animals were already stressed by rapidly changing and rock, throwing debris high into the atmosphere. This debris would have blocked sunlight, causing rapid cooling. The shockwaves would have triggered massive wildfires across entire continents. Any large animals caught in this catastrophe would have had little chance of survival. The smaller animals, those that could burrow underground or survive on seeds and roots, might have had a better chance of waiting out the disaster. This could explain one of the most puzzling aspects of the late Pleistocene extinctions, why they hit large animals so much harder than small ones. It wasn't just random bad luck. The biggest animals, with the highest food requirements and the longest reproduction cycles, would be the first to succumb to a sudden environmental catastrophe. But here's what really gets scientists excited about this theory. If it's true, we should be able to find evidence. Impact events leave very specific signatures in the geological record. They create unique minerals, scatter debris across vast distances, and leave chemical fingerprints that can be detected thousands of years later. And remarkably, scientists have been finding exactly these kinds of signatures in sediment layers that date to the beginning of the Younger Dryas. Coming up next, we'll explore the great cooling mystery itself, how scientists discovered that Earth's climate could change dramatically in less than a human lifetime, and what that meant for every living thing on the planet. Chapter 3: The Great Cooling Mystery. Have you ever wondered what it would feel like if winter just never ended? If summer came, but it was weak and brief, and then winter returned stronger than before? That's essentially what happened 12,900 years ago, but the story of how we discovered this is almost as fascinating as the event itself. Picture this. It's the 1960s, and scientists in Greenland are doing something that seems almost impossible. They're drilling through 2 miles of solid ice, pulling up cylinder after cylinder of frozen history. Each inch of ice core represents years of snowfall, and locked within those frozen layers are secrets about Earth's climate going back over 100,000 years. When researchers first examined these ice cores under microscopes, they expected to see gradual changes, slow transitions between warm and cold periods that matched the gentle orbital cycles that drive ice ages. Instead, they found something that changed our understanding of how climate works forever. What actually happened? Imagine you're living 12,900 years ago. For your entire life, for your parents' lives, and for generations before them, the world had been gradually warming. The massive ice sheets that had covered the landscape were slowly retreating. Rivers ran with meltwater, new valleys opened up, forests crept northward into areas that had been frozen tundra. Your people had adapted to this changing world. You'd learned to hunt new animals as they moved into previously icy territories. You'd discovered new plant foods as forests expanded. Perhaps your tribe had even begun experimenting with staying in one place longer, taking advantage of increasingly predictable seasonal patterns. Then, within your lifetime, maybe even within a few harsh winters, everything changed. The ice began advancing again. Rivers that had run freely for centuries froze solid. The forests your grandparents had watched grow withered and died, replaced by the hardy tundra plants of the deep ice age. Animals you'd never seen before, cold-adapted species, began appearing, while familiar game disappeared or moved south, following the retreating warmth. For people living through it, this wouldn't have been abstract lines on a scientific graph. It would have been pure survival crisis. Food sources that had been reliable for generations suddenly vanished. Shelter strategies that had worked for centuries became inadequate. Migration routes that had been clear were suddenly blocked by advancing ice. But here's what makes this event even more remarkable. It wasn't just a gradual slide back into cold conditions. The ice core evidence shows that the transition was shockingly abrupt. Within perhaps as little as a single decade, the Northern Hemisphere was plunged back into near Ice Age conditions. And then, 1,200 years later, the cold ended just as suddenly as it had begun. The ice cores show another dramatic spike, this time upward, as temperatures rebounded to nearly modern levels in just a few years. It's as if someone had been experimenting with Earth's thermostat, flipping it from Ice Age to warm and back again. This discovery forced scientists to completely rethink how climate systems work. Instead of the slow, predictable changes they had expected, Arctic tundra. In North America, the evidence is written in the sediments of long-vanished lakes. Water levels dropped dramatically. Dust storms scoured the landscape as vegetation died. The Great Plains, which had been developing complex grassland ecosystems, reverted to something resembling the harsh steppes of Siberia. But here's where the story gets really intriguing. While the Northern Hemisphere was freezing, parts of the Southern Hemisphere were experiencing something completely different. In South America, some regions actually got warmer and wetter. In Antarctica, ice cores show a pattern almost opposite to Greenland's, warming when the north cooled, cooling when the north warmed. This bipolar seesaw pattern gave scientists crucial clues about what might have caused such dramatic changes. It suggested that the younger Dryas wasn't caused by something global, like a dimming of the sun or massive volcanic eruptions that would have affected the entire planet equally. Instead, it pointed to something that could reorganize heat distribution between the hemispheres. The most widely accepted explanation involves the ocean currents that carry warm water northward from the tropics. These currents, often called the global conveyor belt, transport enormous amounts of heat around the planet. If something disrupted this system, it could explain how the north could suddenly freeze while the south remained warm. But what could disrupt such a massive system so quickly and completely? One possibility is fresh water. As the great ice sheets melted during the warming period before the younger Dryas, they released enormous volumes of fresh water into the North Atlantic. This fresh water, being less dense than salt water, might have capped the ocean surface, preventing the normal circulation patterns that carry warm water northward. It's an elegant explanation, and computer models show it could work. But there's one problem. Scientists haven't found definitive evidence of the massive freshwater floods this theory requires. That's where our story takes a truly dramatic turn. because some researchers have proposed a completely different explanation, one that involves a visitor from outer space. What if the trigger for the Younger Dryas wasn't gradual ice sheet melting, but a sudden, catastrophic impact? What if a comet or asteroid slammed into the North American ice sheets, vaporizing billions of tons of ice instantly and throwing so much debris into the atmosphere that it triggered rapid cooling, trapped in ice that fell as snow before the pyramids were built? Chapter 4. Reading the Frozen Archives. Imagine holding a piece of frozen history in your hands, ice that fell as snow when your ancestors were just learning to farm, when mammoths still roamed the earth, when the Sahara was green and full of rivers. This isn't fantasy. It's exactly what scientists do when they study ice cores from Greenland and Antarctica. But here's what makes these ice cores truly magical. They don't just tell us about temperature. Locked within each thin layer are tiny bubbles of ancient air, actual samples of the atmosphere from thousands of years ago. When you pop one of these bubbles in a laboratory, you're literally breathing the same air that existed when the Younger Dryas began. The story of how we learned to read these frozen archives is like a detective novel. In the 1960s, researchers knew that ice sheets contained climate information, but they had no idea how detailed that record could be. The first ice cores were crude affairs. Scientists basically took ice saws and cut chunks from glacier surfaces. Then someone had a brilliant idea. What if they drilled straight down, like drilling for oil, but through ice instead of rock? The technology was challenging. Imagine trying to keep a drill bit cool enough to cut ice without melting it, while simultaneously preventing the hole from collapsing as you go deeper. The breakthrough came in the 1970s, when researchers successfully drilled through the entire Greenland ice sheet, over 10,000 feet of solid ice, representing more than 100,000 years of Earth's history. When they brought those first deep ice cores to the surface, they had no idea they were about to revolutionize our understanding of climate. Here's how the magic works. Every year, snow falls on the ice sheets in distinct layers. Winter snow has different chemical properties than summer snow. As years pass, these layers get compressed but remain distinct, like the rings of a tree. By counting the layers, scientists can date the ice with incredible precision. But the real treasure is in the chemistry. The water molecules in snow contain different isotopes, varieties of hydrogen and oxygen that behave slightly differently depending on temperature. When it's colder, more light isotopes end up in the snow. When it's warmer, the ratio shifts toward heavier isotopes. That stunned the scientific community. The climate record was full of sudden jumps and crashes. The isotope ratios would be stable for centuries, then suddenly spike upward or plummet downward in just a few years. These weren't measurement errors. The patterns were too consistent, too dramatic, and too widespread to be anything but real climate changes. The Younger Dryas stood out as the most recent and dramatic of these events. The isotope curves show temperatures dropping by more than 15 degrees Fahrenheit in Greenland in perhaps as little as a single decade. To put that in perspective, that's like the climate of New York suddenly becoming like northern Canada, permanently. But the air bubbles told an even more dramatic story. Methane levels, which reflect the extent of wetlands around the world, collapsed almost instantly. This suggested that the cooling wasn't just affecting Greenland, but was causing wetlands across the northern hemisphere to freeze or dry up. Dust levels in the ice also spiked dramatically, indicating that the landscape had become windier and more arid. Winds were picking up more dust and sand, carrying it all the way to Greenland, where it settled in the snow and became preserved in the ice. The precision of this record is truly remarkable. In some sections of the ice cores, researchers can identify individual years, even individual seasons. They can see the signature of major volcanic eruptions, sulfur spikes that darken the ice, and can be matched to specific eruptions around the world. This precision has allowed scientists to date the beginning of the Younger Dryas to approximately 12,900 years ago, and its end to about 11,700 years ago. But more importantly, it's shown that both the beginning and end of this cold period were shockingly abrupt. As word of these discoveries spread, researchers around the world began looking for evidence of the Younger Dryas in their own records. Marine sediment cores from the Atlantic Ocean showed sudden changes in the tiny shells of plankton, species that prefer cold water suddenly replacing those that prefer warm water. Lake sediments across Europe revealed the collapse of forests almost overnight. Pollen from oak and hazel trees virtually disappears from the record, replaced by hardy Arctic grasses and sedges. Some lakes show signs of actually freezing permanently during the worst of the cold period. But perhaps the most haunting evidence comes from the landscape itself. In valleys across northern Europe, chemical signatures that suggest massive wildfires were burning across continents. This discovery has profound implications. Widespread continental wildfires aren't caused by gradual climate cooling. They're the signature of sudden, catastrophic events, exactly what you might expect if something from space had impacted the Earth. The ice cores have also revealed that the younger Dryas wasn't unique. Scattered throughout the glacial period are dozens of similar events, sudden warming and cooling cycles that reorganized the entire climate system in just a few decades. Scientists call these Dansgaard-Oeschger events, and they suggest that rapid climate change might be more normal than the stable conditions we've experienced for the past 11,000 years. But here's what makes the younger Dryas special. It was the last of these dramatic climate flips, occurring just as the Earth was transitioning out of the Ice Age. It was also the one that coincided most closely with major changes in human culture and the extinction of the megafauna. As we'll discover next, the frozen archives have given us the timeline and the magnitude of this climate crisis, but they've also raised profound questions about what could cause such rapid changes, questions that have led scientists to some truly extraordinary places in their search for answers. Coming up, we'll explore how this climate catastrophe divided the world into two dramatically different hemispheres, and why understanding this division might be the key to solving the mystery of what caused the younger Dryas. Chapter 5. A world divided by ice. Imagine if someone drew a line across the Earth and decreed that everything north of that line would freeze, while everything south would stay warm, or even get warmer. It sounds impossible, but that's essentially what happened during the younger Dryas. This division of the planet into two climate zones gives us crucial clues about what caused this mysterious event. The evidence for this dramatic divide comes from all over the world, and it paints a picture of a planet that seemed to be working against itself. While Greenland was plunging into temperatures colder than those at the North Pole today, Antarctica was actually experiencing one of its warmest periods in thousands of years. Let's travel around the world and see how different regions experienced this global crisis. In northern Europe, the story is written in ancient lake beds and peat bogs. Tree pollen that had been abundant during the warming period before the younger Dryas suddenly had transplanted the landscape of northern Siberia into Central Europe in the span of a few harsh winters. Archaeological sites across Britain tell a haunting story of human adaptation to this crisis. Before the younger Dryas, burial sites are relatively common, suggesting stable populations with time for ritual and ceremony. After the cooling began, these burial sites essentially disappear from the archaeological record for centuries. This doesn't necessarily mean the population died out completely, but it suggests that life became so focused on immediate survival that complex social behaviors like formal burial became impossible luxuries. Meanwhile, across the Atlantic, North America was experiencing its own version of this climate catastrophe. The Great Lakes region, which had been developing rich ecosystems as the ice sheets retreated, suddenly reverted to conditions more like those found today in northern Alaska. Lake levels dropped dramatically as precipitation decreased and evaporation increased despite the cold. Many smaller lakes dried up entirely, their beds becoming sources of dust that was picked up by increasingly strong winds and carried across the continent. But here's where the story gets really interesting. While all of this freezing and drying was happening in the north, the southern hemisphere was experiencing something completely different. In South America, many regions actually became warmer and wetter during the younger Dryas. The Amazon rainforest expanded. Glaciers in the Andes began retreating faster than they had before. Some lake levels actually rose as increased rainfall filled basins that had been dry. Antarctica tells the most dramatic story of all. Ice cores from the South Pole show a warming trend that began almost exactly when Greenland began cooling. It's as if the two hemispheres were connected by a giant seesaw. When one went down, the other went up. This pattern isn't random. It's the signature of a fundamental reorganization of how heat moves around the planet. Earth's climate system is driven by ocean currents that transport warm water from the tropics toward the poles. In the modern world, warm water flows northward in the Atlantic, heating Europe and the northern Atlantic region, then cools and sinks, returning southward as cold, deep water. During the Younger Dryas, something disrupted this system. The northward flow of warm water either slowed dramatically or stopped entirely. This meant that heat that would normally warm the northern hemisphere, normal circulation patterns. It's a plausible explanation, and computer models show it could work, but there's a problem. Despite decades of searching, scientists haven't found definitive evidence of the truly massive freshwater floods this theory requires. That's where some researchers have proposed a much more dramatic alternative. What if the disruption wasn't caused by gradual ice melting, but by a sudden, catastrophic event, like a cosmic impact? Imagine a comet fragment a mile or more across slamming into the Laurentide ice sheet, which at the time covered most of eastern Canada and the northern United States. The impact would have instantly vaporized billions of tons of ice, creating a massive steam explosion that would have injected enormous amounts of fresh water directly into the North Atlantic. But the effects wouldn't stop there. The impact would have thrown debris high into the atmosphere, creating a dust cloud that could have blocked sunlight for months or even years. This would have caused rapid cooling across the northern hemisphere, while having much less effect on the southern hemisphere. The impact would also have triggered massive wildfires across North America. The heat and shock waves from the explosion would have ignited forests across entire continents. The smoke from these fires would have added to the atmospheric dust, creating a feedback loop of cooling and darkness. This could explain one of the most puzzling aspects of the Younger Dryas: why it hit the northern hemisphere so much harder than the southern hemisphere. An impact in the northern ice sheets would have had immediate and devastating local effects, while the southern hemisphere would have been largely shielded from the direct consequences. Evidence for this impact hypothesis has been building for years. Researchers have found layers of sediment dating to the beginning of the Younger Dryas that contain unusual materials, microscopic diamonds, metallic spherules, and elevated levels of platinum group elements that are rare on Earth but common in asteroids and comets. These materials have been found at sites across North America, Europe, and even Asia, suggesting that whatever caused them was truly global in scope. But the concentrations are highest in North America, consistent with an impact somewhere on that continent. The debate over what caused the Younger Dryas continues to rage in scientific circles. Traditional climate scientists argue that the ocean circulation changes could have been triggered by more gradual processes. Impact researchers counter that only a cosmic catastrophe could explain the speed and Earth just before this catastrophe struck, and discover why their sudden disappearance remains one of paleontology's greatest mysteries. Chapter 6. The Last Hunt of the Mammoth Kings. Picture the most incredible wildlife documentary you've ever seen, but imagine it's happening on your own continent just 13,000 years ago. Herds of woolly mammoths thunder across grasslands that stretch from horizon to horizon. Saber-toothed cats with fangs like curved daggers stalk through forests. Giant ground sloths, the size of elephants, browse on tree branches, completely unaware that they're living in the final chapter of their species' story. This was the world that existed just before the Younger Dryas began, a world so rich in megafauna that it's almost impossible for us to imagine today. These weren't just big animals. They were ecosystem engineers that shaped entire continents through their feeding, migration, and daily activities. The woolly mammoth was perhaps the most magnificent of all. Standing up to 11 feet tall at the shoulder and weighing as much as 6 tons, these creatures were perfectly adapted to Ice Age conditions. Their thick fur coats could keep them warm in temperatures that would kill a modern elephant. Their curved tusks, some over 13 feet long, were tools for clearing snow, fighting rivals, and attracting mates. But mammoths weren't just surviving, they were thriving. Genetic studies of mammoth DNA show that their populations had remained stable for hundreds of thousands of years. They had survived multiple ice ages, volcanic eruptions, and dramatic climate shifts. They were ultimate survivors, perfectly adapted to their world. So what could possibly drive such successful creatures to extinction? The story becomes even more mysterious when we look at the timing. Across North America, mammoth populations seem to have collapsed almost simultaneously around 12,900 years ago, exactly when the Younger Dryas cooling began. But this wasn't a gradual decline over centuries. Radiocarbon dating of mammoth bones shows that they disappeared from most of their range within just a few hundred years. The saber-toothed cats tell a similar story. Smilodon fatalis, the most famous of the saber-toothed species, had been the apex predator of North America for over 1 million years. These cats were built like linebackers, with incredibly powerful forelimbs designed to wrestle down prey much larger than themselves. Their famous fangs weren't just for show, they were larger than modern elephants, and could rear up on their hind legs to reach tree branches 20 feet off the ground. Their massive claws, some over 1 foot long, could strip bark from trees or dig enormous burrows. In some caves in the American Southwest, paleontologists have found layers of giant sloth dung stacked yard after yard deep, the accumulated droppings of thousands of years of occupation. Then, suddenly, the dung layers stop. The caves were abandoned, and the sloths disappeared forever. But here's what makes this extinction event truly puzzling. It was selective in a very specific way. The victims were almost exclusively large animals, those weighing more than about 100 pounds. Smaller animals, rabbits, squirrels, birds, fish, survived the transition with minimal losses. This size-selective pattern has led to one of paleontology's most heated debates. If climate change was the primary cause, why didn't it affect all animals equally? Climate changes in the past had caused some extinctions, but nothing approaching the scale of what happened at the end of the Pleistocene. That's where human hunting enters the story. Around the time these animals were disappearing, human populations were spreading across the Americas and developing increasingly sophisticated hunting technologies. The Clovis culture, known for their beautifully crafted spear points, appeared in the archaeological record at almost exactly the same time as the megafauna extinctions. Could a few thousand Stone Age hunters really have driven species that numbered in the millions to complete extinction? It seems impossible, but computer models suggest it might have been feasible under certain conditions. The key factor is that these animals had never encountered human hunters before. They had no instinctive fear of humans and no behavioral adaptations to avoid human predation. Modern elephants and rhinos are wary and dangerous precisely because they evolved alongside human ancestors in Africa. But American megafauna were naive. They probably approached human hunters with curiosity rather than fear. Add to this the fact that large animals reproduce slowly. A mammoth female might produce only one calf every few years, and that calf required years to reach maturity. If human hunting increased adult mortality even slightly, it could drive populations into a death spiral from which they couldn't recover. But the timing still bothers many researchers. Why would human hunting suddenly become so effective right at the moment when the climate was changing dramatically? That's where the cosmic impact hypothesis offers an intriguing smaller creatures. The secondary effects would have been even worse. Impact-triggered wildfires would have destroyed vast areas of habitat. The atmospheric dust and debris would have blocked sunlight, causing plant die-offs that would have eliminated the food base for large herbivores. This could explain the selectivity of the extinctions. Large animals would have been hit hardest by both the immediate impact effects and the subsequent ecological collapse. Smaller animals, especially those that could burrow underground or survive on seeds and insects, would have had a much better chance of surviving the catastrophe. Recent discoveries have added weight to this impact hypothesis. At several archaeological sites across North America, researchers have found layers of sediment dating to exactly the beginning of the Younger Dryas that contain evidence of massive wildfires, unusual minerals, and even what appear to be impact materials. At the Abu Huraira site in Syria, archaeologists found a layer containing glass spherules and other materials that appear to have formed at extremely high temperatures, consistent with either impact or proximity to massive fires. Similar materials have been found at sites in North America, Europe, and even Asia. But perhaps the most intriguing evidence comes from Greenland ice cores. Researchers have found elevated levels of platinum and other rare metals in ice layers dating to the beginning of the Younger Dryas. These metals are rare in Earth's crust, but common in asteroids and comets. The debate continues, but one thing is clear. The world that emerged from the Younger Dryas was fundamentally different from the one that entered it. The age of giants was over. The ecosystems that had supported mammoths, saber-toothed cats, and giant sloths were gone forever. This transformation had profound implications for the humans who survived it. Without large game animals to hunt, human cultures had to adapt rapidly. Some turned to smaller prey and intensive foraging. Others began the experiments with plant cultivation that would eventually lead to agriculture. Coming up next, we'll explore how human societies around the world responded to this crisis and discover how some of humanity's most important innovations might have emerged from the ashes of catastrophe. Chapter 7: Survivors in a Changing World. Imagine waking up one morning to discover that the world you've known your entire life has fundamentally changed overnight. The animals your people have hunted for generations have vanished. The plants you've gathered for food no longer. Millennia to come. But here's what's remarkable about this story. Humans didn't just survive this catastrophe. In many cases, they emerged from it with innovations and social developments that laid the foundation for civilization itself. Let's start with one of the most famous archaeological cultures of this period, the Clovis people of North America. These skilled hunters had developed a sophisticated toolkit centered around their distinctive fluted spear points, beautifully crafted stone weapons that were perfectly designed for hunting the megafauna of the late Pleistocene. Clovis points have been found from coast to coast across North America, suggesting either rapid migration of these people or widespread adoption of their hunting technology. For several centuries, this culture flourished, taking advantage of the rich hunting opportunities provided by mammoth herds and other large game. Then, almost as suddenly as they had appeared, the classic Clovis culture vanished from the archaeological record. The distinctive fluted points stopped appearing at sites across the continent. The specialized mammoth hunting toolkit was abandoned. For years, archaeologists debated what this disappearance meant. Had the Clovis people themselves gone extinct? Had they been replaced by other groups? The answer, it turns out, is more complex and more hopeful than either of these scenarios. Recent archaeological evidence suggests that the Clovis people didn't disappear, they aside. They adapted. As the megafauna they specialized in hunting went extinct during the Younger Dryas, these communities rapidly developed new survival strategies. In the Great Plains, post-Clovis groups began focusing on bison hunting, developing new types of spear points better suited to these smaller but more agile prey animals. Along the coasts, communities turned to marine resources, becoming some of the world's first specialized fishers and shellfish gatherers. In the southeastern United States, groups began intensively harvesting nuts, seeds, and other plant foods, developing the early stages of plant management that would eventually lead to agriculture in this region. This rapid cultural adaptation shows something crucial about human nature. We are perhaps the most adaptable species that has ever lived. When our environment changes dramatically, we don't just try to maintain old ways of living. We innovate, experiment, and develop entirely new approaches to survival. When the Younger Dryas cooling began, this region became drier and less productive. The wild wheat and barley stands that the Natufians had been harvesting began to fail. Some settlements were abandoned as communities returned to more mobile lifestyles. But in a few locations, something remarkable happened. Instead of abandoning their experiments with sedentism, some Natufian communities doubled down on their investment in plant foods. They began not just harvesting wild grains, but actively planting and tending them. This was the birth of agriculture, not as a leisurely innovation by well-fed foragers, but as a desperate adaptation to environmental crisis. The Younger Dryas didn't prevent the development of farming, it accelerated it. Archaeological sites from this period show clear evidence of this transition. Storage pits become larger and more elaborate, suggesting communities were investing more heavily in preserving harvested grains. Stone tools show increasing specialization for grain processing. Most remarkably, the grains themselves begin to show signs of domestication, genetic changes that occur only when plants are being actively selected and replanted by humans. Similar patterns appear around the world. In China, communities began intensively harvesting and eventually cultivating rice and millet during this same period. In the Andes Mountains of South America, groups began the domestication of potatoes and other highland crops. It's as if the crisis of the Younger Dryas forced human communities everywhere to reconsider their relationship with the natural world. Instead of simply taking what nature provided, they began actively shaping and managing their environments. But adaptation wasn't always successful, and the archaeological record preserves haunting evidence of communities that didn't survive the transition. In northern Europe, some settlements show signs of rapid abandonment around the beginning of the Younger Dryas. Hearths are left with food still in cooking pots, tools are scattered as if dropped in haste. These sites suggest that some communities simply couldn't adapt quickly enough to the changing conditions. In Britain, the archaeological record shows a particularly dramatic pattern. Before the Younger Dryas, burial sites are relatively common, suggesting stable populations with time for complex ritual behaviours. During the coldest centuries of the event, formal burials essentially disappear from the record. This doesn't necessarily mean the population died out completely, but it's conditions. Perhaps most remarkably, some communities used the crisis as an opportunity for innovation in social organisation. Archaeological evidence suggests that trade networks actually expanded during the Younger Dryas, as communities specialised in different survival strategies and exchanged goods over long distances. This makes sense when you think about it. In times of environmental instability, having connections to resources in different regions could mean the difference between survival and extinction. Communities that could trade surplus fish for grain, or stone tools for animal hides, had a significant advantage over those that remained isolated. The genetic evidence also tells a story of survival and adaptation. DNA studies of modern populations show that virtually all human lineages that existed before the Younger Dryas also exist today. This crisis didn't cause human extinctions on the scale that it caused megafauna extinctions. Instead, it caused cultural extinctions and innovations. Ways of life that had persisted for millennia vanished in a few centuries, while entirely new approaches to survival emerged from the ashes of the old. Coming up next, we'll explore the most controversial explanation for what caused this global catastrophe: the theory that a visitor from outer space changed the course of Earth's history in a single, catastrophic day. Chapter 8: The Cosmic Visitor Theory. What if I told you that on a clear morning 12,900 years ago, people across North America looked up to see multiple streaks of fire tearing across the sky? What if those streaks weren't meteors burning up harmlessly in the atmosphere, but fragments of a massive comet about to change the course of Earth's history forever? This is the cosmic impact hypothesis, one of the most controversial and fascinating explanations for what triggered the Younger Dryas cooling and the extinction of the megafauna. It sounds like science fiction, but the evidence supporting it has been building steadily for over a decade. The story begins with a simple observation that bothered scientists for years. The Younger Dryas cooling began too suddenly to be explained by gradual climate processes. Even rapid changes in ocean circulation should take decades or centuries to fully develop. But the ice core evidence suggested the cooling began in just a few years, possibly even less. That kind of speed demands the realization that a massive asteroid impact had triggered the dinosaur extinction. The evidence was overwhelming: shocked quartz crystals that form only under extreme pressure, spherules of vaporized rock scattered across continents, and soot layers indicating planet-wide wildfires. Once scientists knew what to look for, they began finding evidence of other impact events throughout Earth's history. Some had triggered mass extinctions, others had caused more regional effects, but all left distinctive calling cards in the geological record. In 2007, a team of researchers led by Richard Firestone made a startling announcement. They claimed to have found similar impact signatures in sediment layers dating to exactly the beginning of the Younger Dryas. At sites across North America, they had discovered a black mat, a dark layer of sediment containing high concentrations of charcoal, suggesting massive wildfires. But this wasn't ordinary charcoal. Mixed in with the burned organic matter were tiny diamonds, metallic spherules, and elevated levels of platinum group elements. These materials don't form under normal Earth conditions. The diamonds, called nanodiamonds, require the extreme pressures and temperatures that occur during cosmic impacts or nuclear explosions. The metallic spherules appear to have condensed from a vapor phase, exactly what you'd expect if rock had been vaporized by an enormous explosion. Most intriguingly, the platinum group elements found in these layers have isotopic ratios that match those found in certain types of meteorites and comets, but differ from typical Earth materials. As word of these discoveries spread, other research teams began looking for similar evidence around the world. Remarkably, they began finding it. Impact signatures dating to the beginning of the Younger Dryas have now been reported from sites in Europe, Asia, and even South America. But the most compelling evidence might be coming from an unexpected source: ancient human settlements. At Abu Huraira, an archaeological site in northern Syria that was inhabited continuously for thousands of years, researchers found something extraordinary in the layers dating to the beginning of the Younger Dryas. Mixed in with the normal archaeological debris were thousands of tiny glass and metal spherules that appear to have formed at temperatures exceeding 2000 degrees Celsius. These spherules contain metallic elements in combinations that don't occur naturally on Earth's surface. Some contain microscopic diamonds, others show evidence of having been rapidly archaeological layer, not concentrated in specific areas as you'd expect if they came from nearby fires. This suggests they fell from the sky like rain, blanketing the entire settlement. Similar discoveries have been made at archaeological sites across North America. At the Murray Springs site in Arizona, researchers found a layer containing impact spherules directly overlying the latest Clovis artifacts. At Blackwater Draw in New Mexico, the same pattern appears. The timing is striking. These impact signatures appear at archaeological sites at exactly the moment when Clovis culture disappears from the record and megafauna extinctions accelerate. But perhaps the most dramatic evidence comes from the ice caps themselves. Researchers analysing Greenland ice cores have found elevated levels of platinum and other rare metals in layers dating to the beginning of the Younger Dryas. These metals are extremely rare in Earth's crust, but common in asteroids and comets. Their presence in Greenland ice suggests that debris from a cosmic impact was distributed globally in the atmosphere and eventually settled out in snow that accumulated on the ice caps. The pattern of evidence has led researchers to propose a specific scenario for what might have happened. A large comet, perhaps 4 kilometers across, approached Earth on a trajectory that brought it into collision with the Laurentide ice sheet covering much of North America. The comet didn't survive intact to create a single large crater. Instead, it broke apart in the atmosphere, creating multiple impacts across the ice sheet and setting off a chain of catastrophic effects. The immediate impacts would have vaporized billions of tons of ice, creating massive steam explosions that injected enormous amounts of water vapor into the atmosphere. The shock waves would have triggered earthquakes and volcanic eruptions. Most importantly, the impacts would have destabilized the ice sheet, causing massive floods of meltwater into the North Atlantic. But the effects wouldn't have stopped there. The heat from the impacts would have ignited wildfires across entire continents. The debris thrown into the atmosphere would have created a dust cloud that blocked sunlight, causing rapid cooling. For large animals, this would have been a perfect storm of catastrophe. The immediate thermal effects would have killed many directly. The atmospheric dust would have caused plant die-offs that eliminated food sources. The fires would have destroyed vast areas of habitat. This could explain why the catastrophe directly. The materials found there indicate temperatures hot enough to melt rock, exactly what you might expect if people were living near the impact zone. Yet despite the growing evidence, the cosmic impact hypothesis remains controversial. Critics point out that no definitive impact crater has been found, though supporters argue that impacts on ice sheets might not leave permanent craters. More problematically, some researchers have been unable to reproduce the findings of impact materials at certain sites, leading to questions about whether some of the evidence might have alternative explanations. The debate continues, but one thing is clear. Something triggered the most rapid climate change in Earth's recent history 12,900 years ago. Whether that something was a cosmic visitor or a more terrestrial process, the effects were global and dramatic. Coming up next, we'll explore some of the most intriguing archaeological evidence for this cosmic catastrophe, including ancient settlements that seem to have been abandoned overnight, and mysterious layers of sediment that appear on 3 continents. Chapter 9: Cities of Secrets Beneath the Earth. Imagine being an archaeologist excavating an ancient settlement. carefully brushing away thousands of years of accumulated dirt and debris. Layer by layer, you're uncovering the story of people who lived and died millennia ago. Then suddenly, your brush reveals something that shouldn't exist. Tiny spheres of glass and metal that could only have formed in temperatures hot enough to melt rock. This is exactly what happened to researchers working at archaeological sites around the world, and what they found has revolutionized our understanding of what might have occurred 12,900 years ago. The story begins at a site called Abu Huraira in northern Syria. For decades, this has been one of the most important archaeological sites in the world because it preserves evidence of humanity's transition from hunting and gathering to agriculture. People lived at Abu Huraira continuously for thousands of years, leaving behind layers of artifacts, food remains, and building foundations that tell the story of this crucial transformation. But when researchers began examining the layers dating to around 12,900 years ago, they found something completely unexpected. Mixed in with the normal archaeological debris, broken pottery, stone tools, animal bones, were thousands of tiny glass spherules that didn't belong in an ancient village. These spherules were no bigger than grains of sand, but they contained and chromium in ratios that don't occur naturally in Earth's crustal rocks. Some contained microscopic diamonds, others showed clear evidence of having been rapidly cooled from a molten state. The only known processes that can create such materials are cosmic impacts, nuclear explosions, or extreme proximity to fires hot enough to melt rock. Since nuclear weapons didn't exist 12,900 years ago, that left only impacts or fires as possibilities. But the distribution of the spherules ruled out normal fires. They were scattered throughout the archaeological layer, not concentrated near hearths or other obvious fire sources. They appeared to have fallen from the sky like rain, blanketing the entire settlement. What makes Abu Huraira even more intriguing is what happened to the people living there. The archaeological evidence shows that this thriving community was suddenly abandoned right around the time these mysterious spherules appeared. A settlement that had been continuously occupied for thousands of years was deserted almost overnight. The timing is crucial. Abu Huraira sits in the northern part of Syria, in a region that would have been directly affected by climate changes in the North Atlantic. If a cosmic impact had disrupted ocean circulation and triggered the younger Dryas cooling, communities in this region would have been among the first to feel the effects. But Abu Huraira isn't the only site with this kind of evidence. Researchers have now found similar impact signatures at archaeological sites across 3 continents. At Murray Springs in Arizona, excavations have revealed a distinctive black layer containing impact spherules, nanodiamonds, and elevated levels of rare metals. This layer sits directly on top of the latest Clovis artifacts found at the site, the last evidence of this sophisticated hunting culture before it disappeared from the archaeological record. At Blackwater Draw in New Mexico, another famous Clovis site, researchers found the same pattern. A dark layer containing impact materials marks the end of the Clovis occupation and the beginning of the Younger Dryas cooling. These discoveries are particularly significant because they directly link the proposed cosmic impact to changes in human culture. The Clovis people were highly sophisticated hunters who had developed specialized tools for taking down megafauna. Their sudden disappearance from the period. At Baffin Bay in northwest Greenland, researchers drilling marine sediment cores found elevated levels of platinum and other rare metals in layers dating to the beginning of the Younger Dryas. These metals are extremely uncommon in Earth's crustal rocks, but abundant in asteroids and comets. The Baffin Bay discovery is particularly important because it's located far from any potential terrestrial source of these materials. The only reasonable explanation for their presence is that they settled out of the atmosphere after being distributed globally by some catastrophic event. Similar discoveries have been made in lake sediments across North America and Europe. At sites from California to the Carolinas, from Britain to Belgium, researchers have found the same signature, a dark layer containing impact materials dating to exactly 12,900 years ago. One of the most remarkable aspects of these discoveries is their consistency. Despite being separated by thousands of miles, sites across multiple continents show the same pattern of evidence at the same time. This suggests that whatever caused these signatures was truly global in scope. The spherules found at these sites show particularly intriguing characteristics. Many contain metallic compositions that match certain types of meteorites, particularly those rich in iron and nickel. Others contain rare minerals that form only under the extreme conditions created by cosmic impacts. Perhaps most significantly, many of the spherules show evidence of having been created in an oxygen-rich environment, exactly what you'd expect if they formed when a comet or asteroid vaporized ice and organic matter during impact with Earth's surface. Computer modeling has helped researchers understand how such widespread distribution of impact materials could occur. When a large object hits Earth at cosmic speeds, it doesn't just create a crater, it vaporizes both the impactor and target material, creating a fireball that can reach temperatures of thousands of degrees. This vaporized material expands rapidly into the atmosphere, where it condenses into tiny droplets that solidify as they cool. These droplets, the spherules found at archaeological sites, can be carried by atmospheric winds and distributed across entire continents before settling to the ground. The modeling shows that an impact large enough to trigger the climate changes associated with the younger Dryas would also be large enough to distribute debris globally. The pattern of evidence found at archaeological and geological sites matches these predictions remarkably well. Brighter than the sun. Feeling the ground shake from impacts hundreds of miles away, watching as debris rained from the sky and wildfires swept across the landscape. For people with no understanding of cosmic impacts or global climate systems, this would have been beyond comprehension. Yet some survived. The archaeological record shows that while many settlements were abandoned during the early stages of the Younger Dryas, humans persisted and eventually adapted to the new conditions. They developed new survival strategies, new technologies, and new ways of organizing their societies. Coming up next, we'll explore the heated scientific debate surrounding this cosmic impact hypothesis and discover why some of the world's most respected researchers are locked in a battle over evidence that could rewrite our understanding of human history. Chapter 10. The Great Debate Rages On. Science, at its best, is a battleground of ideas, where evidence is the only weapon that matters, and the truth emerges from the clash of competing theories. Nowhere is this more apparent than in the raging debate over what caused the Younger Dryas, a debate that has divided the scientific community and sparked some of the most heated controversies in modern archaeology and climate science. On one side are the impact hypothesis supporters, armed with their nanodiamonds, platinum anomalies, and mysterious spherules. On the other are traditional climate scientists, pointing to the lack of a definitive impact crater and questioning whether some of the supposed impact evidence might have more mundane explanations. The battle lines were drawn in 2007, when Richard Firestone and his colleagues first announced their discovery of impact signatures at sites across North America. The initial reaction from the scientific community was skeptical, and for good reason. Extraordinary claims require extraordinary evidence, and the idea that a cosmic impact had triggered one of the most important events in recent Earth history was certainly extraordinary. The first wave of criticism focused on the supposed impact materials themselves. Skeptics argued that nanodiamonds could form through natural processes like wildfires or geological activity. They pointed out that platinum and other rare metals could be concentrated by biological processes or contamination from modern sources. More problematically, when other research teams tried to replicate the findings at some of the original sites, they couldn't find the same impact signatures. This reproducibility crisis had been misinterpreted, but impact hypothesis supporters fought back with new discoveries and refined methods. They argued that their critics were using inadequate sampling techniques and looking in the wrong places. They pointed to consistent patterns of evidence at sites around the world, arguing that such widespread distribution couldn't be explained by local processes. The discovery of the Abu Huraira spherules added new fuel to the fire. Here was direct evidence from an archaeological site showing that ancient humans had witnessed something catastrophic enough to create glass spherules at temperatures exceeding 2000 degrees Celsius. The spherule's unusual metallic compositions and the presence of microscopic diamonds seem to rule out normal explanations like hearth fires or volcanic activity. Critics responded by suggesting alternative formation mechanisms, but none could fully explain the unusual chemistry and widespread distribution of these materials. Perhaps most significantly, the Abu Huraira discovery demonstrated that whatever had created these spherules had directly affected human communities. This wasn't just abstract geological evidence, it was proof that ancient people had experienced something extraordinary. The debate took another turn when researchers began finding impact signatures in ice cores from Greenland. The elevated levels of platinum and other rare metals found in ice layers dating to the beginning of the Younger Dryas provided independent confirmation that something unusual had occurred at exactly the right time. Ice cores are particularly valuable evidence because they're less likely to be contaminated than surface sites. The ice acts as a natural archive, preserving the atmospheric chemistry of ancient times. Finding impact signatures in multiple ice cores from different locations strengthened the case considerably. But critics weren't convinced. They argued that the metal concentrations in ice cores, while unusual, weren't necessarily evidence of cosmic impact. They suggested that volcanic activity or other terrestrial processes could have injected these materials into the atmosphere. The missing crater remained the biggest problem for impact supporters. Every confirmed large impact in Earth's history has left a crater, yet despite extensive searching, no definitive Younger Dryas impact crater has been found. Impact supporters have proposed several explanations for this absence. They argue that impacts on ice sheets might not leave permanent craters, since the ice would eventually melt and flow away. They also suggest that the impacts might have occurred over water, where craters were, with many geologists arguing that these features form through normal geological processes. The debate has also revealed deeper philosophical divisions within the scientific community. Impact supporters tend to favour catastrophic explanations for major changes in Earth's history. They point to the growing recognition that catastrophic events, asteroid impacts, massive volcanic eruptions, rapid climate changes, have played crucial roles in shaping our planet's development. Their critics tend to favour more gradual explanations, arguing that most geological and climatic changes can be understood through uniformitarian processes, the same forces we observe operating today, acting over long periods of time. This philosophical divide reflects a broader tension in earth sciences between catastrophism and uniformitarianism that dates back to the early days of geology. The acceptance of the asteroid impact theory for dinosaur extinction shifted the balance somewhat toward catastrophism, but the scientific community remains generally skeptical of dramatic, catastrophic explanations. The Younger Dryas impact debate has also been complicated by its implications for human history. If a cosmic impact really did trigger this event, it would mean that human cultural development has been shaped by cosmic accidents in ways we've never fully appreciated. The end of Clovis culture, the extinction of the megafauna, even the development of agriculture might all be connected to a chance encounter with a comet. This gives human history a contingent quality that makes some researchers uncomfortable. As the debate has continued, both sides have refined their arguments and gathered new evidence. Impact supporters have developed more sophisticated methods for identifying and analysing impact materials. They found evidence at an increasing number of sites around the world, building a case for a truly global catastrophe. Critics have responded by developing alternative explanations for some of the evidence, while maintaining their skepticism about the overall hypothesis. They've pointed to the complexity of Earth's climate system, arguing that the Younger Dryas could have been triggered by more subtle changes in ocean circulation or atmospheric composition. Recent developments have added new complexity to the debate. Some researchers have proposed that the impact hypothesis and traditional climate explanations aren't mutually exclusive. They suggest that a cosmic impact might have provided the trigger for changes in ocean circulation that were already primed to occur. This hybrid model could explain both the sudden onset of the Younger Dryas and the lack of. This controversy has pushed researchers to develop better methods for studying ancient catastrophes and has deepened our understanding of how Earth's climate system responds to sudden perturbations. Coming up next, we'll explore how the Younger Dryas fits into larger patterns of climate change and discover why understanding these patterns might be crucial for predicting our planet's future.